In today's lesson, we are going to be talking about set basics. And what we're going to be doing today in particular is we are going to start by defining a set. And we are going to describe and interpret empty and universal sets. We are going to count cardinalities of sets. We're going to discuss set/element containment of sets. So like in some sets, we might be able to say that there is like another set within that. Then we're going to talk about specifics, and we're going to be constructing sets given sets of conditions. And then we are going to perform operations on sets. So first, we're going to need to define our set. So the way that we define a set, it is a collection of distinct objects. The way that we use a notation for this, we use a curly bracket, okay? And whatever is contained in the set goes into that curly bracket. As an example, you could say the set capital A. Capital letters are typically used to denote sets. We could say pi B, C, okay? The way that we define an element is it is a distinct object making up a set. So what we would say here is pi, this little symbol here means belongs to, is an element of A. B is an element of A. And C is an element of A. Now, if I had something like D, well, D is not an element of A. D is not something inside of A. Okay? Now, there are three ways that we can define a set. We can define a set in words. So like a perfectly good set, we could say the set of all even numbers. Okay, well, we know what we're talking about there. So we have the set of all even numbers. So like 2, 4, 6, 8, 468, whatever. These are all the sets of, these are all elements of the set containing all even numbers. All right. Boop, boop. Another way that we could define a set is as a list. So if I refer back to my example, I can quite literally say set 2, 4, 6, 8. And one thing that is used a lot in mathematics, in particular set theory, is the ellipsis, ... because we know what the pattern is at this point. Okay. The other thing we can use is what's called set builder notation. Set builder notation is really, really cool when you're writing collections of numbers where the collection is really big. I would say the set of X, and there's two ways that I could do this. I could either use a colon or a vertical line, but they both mean the same thing. The set of X such that we could say X is even. Boom. That's another way that I could write a set. There's three different ways that I can write sets. I can write them in words, I can write them as a list, and I can use set builder notation. Empty set or null set, they're basically the same thing, but context is important. The empty set, the way that we write that is it's a set of curly braces with nothing in it. The null set, it's a 0 with a slash through it. What these are, it's saying the same thing here. This is a set containing yeah, no elements. Okay, a set containing no elements. If we can have a set with elements in it, certainly we could have a set with no elements. Further, this is what we call the universal set. It's like a big old cursive U. This is the set containing all the elements. Whoa, 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 whoa. Come on back now. How does that work? So let's suppose, for example, I had all of the numbers. And let's even just say all of the integers, right? 1, 2, 3, 4, 5. And let's suppose I defined the set B somewhere in this space. And let's say B is 6 through 100. So we've got 6, 7, 8, all this stuff in there. And everybody outside of that, you know, okay, cool. So what I would say here for the set U, let's suppose that the biggest thing in here was 107. What the set U would be, this is the universal set, would be 1, 2, the old ellipsis, up to 107. The set B would be 6, 7, all the way up to 100. You're going to see in the notes I use some different examples. I think that mathematical examples are easier to think about, but different strokes, different folks. Take a look at the examples from the notes if you want to see some like examples of majors or people or whatever the case may be. Now, cardinality. So the way we define cardinality, it is the number. That's number, not a pound sign, not a hashtag, of elements in a set. So the way that we typically denote this is n of set equals number. Okay, so whatever the set is, I want to know the number of things in it, and I should get out an integer. I should get out a finite number. So let's consider the set A. I've got Q, R, S, T, U, and V. That's 1, 2, 3, 4, 5, 6. So n of A is 6. Here I've got 1, 2, 3 things. So n of B, well, that's going to be 3. Okay. Now, the complement of a set. This is an interesting one. This is all elements in the universe, but not, not get too weird with it here. But not in a set A. Nope, not yet. Goodness gracious. All elements in the universe, but are not in the set A, is the complement of A, and we write that as A raised to the C power. That means A complement. So the way you could think about it is if this is my universe, and I've got this set A here in the universe, everyone that's not in A, but is obviously in the universe, is in A complement. Okay. So, some really great examples. Nope, not a highlighter. Don't do that. So, let's say I want to define what A complement was, and always read this as A complement. Don't read this as AC, read this as A complement. I define the universe to be the set A, B, C, D, and the set capital A to be A. So what is capital A complement? Well, what's everything that's in the universe that's not in A? Well, this thing is in A. So it's got to be in the universe, but not in A. So it's going to be the elements B, C, and D. What about BC? Well, I know that BC is 2, 4, 6. So what I'm going to do is in the set U, I'm going to drop out 2, 4, and 6, and blah, blah, blah. Well, this is tricky because in U, I've used this ellipsis. So that means I'm talking about all the integers here. So what B complement is going to be is 1, 3, 5, dot, dot, dot. What I'm really saying is B complement is all odd numbers. Which makes sense because what I'm saying about B is all even numbers. U is all of the integers. So what are all the integers that aren't even? Well, those are the odd ones. Okay. Let's suppose I define U, my universe, to be A, B, C, D. And I said A is little a, find the cardinality of AC. Well, I already know that AC is this set here. How many elements are there in the set? B, C, D. So N of AC, well, that's going to end up being 3. How many elements are there? As a note, let me just make sure that this is clear. Bloop. The cardinality of NAC, that's the number of elements in the universe minus the number of elements in A. Okay? The number of elements in the universe minus the number of elements in A. That's everyone that's not in A. Okay? Equality of sets. 2 sets are equal if and only if both sets contain the exact same elements. Okay, that's when 2 sets are equal. So set equality is kind of a tough thing to talk about. But let's suppose I had sets A and B. And let's suppose A was 1, 2, 3, B, N, capital K. And let's suppose B is N. Goodness. No. Suppose cap B was N, 2, 3, 1, B, capital K. Is it true that A equals B? Well, yes, because there's a 1 in both of them, there's a 2 in both of them, there's a 3 in both of them, there's a B in both of them, there's an N in both of them, and there's a K in both of them. Fine. Now, if I were to go and drop this 2 out of A, well then all of a sudden, if I were to ask the question, well, is A equal to B? The answer is no, they are not. Because there is something that's in B that's not in A, right? And that's a big deal. Doesn't seem like it'd be a big deal, but equality of sets is a really special thing, okay? There are 2 rules to remember when working with sets, and it doesn't seem too far-fetched, but it'll come back to our original definition. The first thing we want to drive home is the order of elements doesn't matter. Okay, we saw that in this example here. When I put the 2 back in this guy, boop, 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 now it's equal. You see that these were equal even though they were written in different orders. It doesn't matter The way we define set is it is a collection of distinct objects. The objects in B are no less distinct than they are in A because we wrote them in a different order. We're not ranking these things, we're just stating that's what they are. Okay. The other thing, and this is kind of an odd one, but it's an important rule to keep in mind, is we should not allow repeats of elements. It seems silly, but let's suppose I had the set A was 1, 1, 2, 3, 4, 5, 5, 5. The way that I would actually define the set A, sorry, my computer's trying to die on me. Okay, the way I would actually define the set A is I would just say it's 1, 2, 3, 4, 5. I would just go ahead and rewrite it where I've dropped out the repeats. And it's important to realize this because if I were to write the cardinality of A, for this set, even what I'm really doing is I'm counting the number of distinct elements. Well, there's 1, 2, 3, 4, 5 distinct elements. So it's better to write it this way. It makes cardinality a little bit easier to discern. Now, let's talk about containment. So there's two types of containment with sets. First of which is subset. This is how we write it. It's like the inequality sign. It's just loopy instead of hard. And there's no corner on it. It can't cut you. The way a subset works is we would say A is a subset of B if every element in A is also an element of B. Okay. Now, we would write this as A is a subset of B. And a way you could think about this is if I had A, B is wholly contained in it. So what really isn't happening is, let's suppose I had A, and then let's say that B had something kind of pop outside of it. This right here, this is not containment. This is not a subset. Okay. Now, this seems a little weird, but there's what's called a proper subset. Now, here's the way a proper subset works. A subset not equal to the original set is a proper subset. Not equal to. Okay, so in this example, right, when we look at this picture, B is contained inside of A, but they aren't the same. So let's suppose I had something like this. And let's just start with a really small example. Let's suppose A was equal to A, B, C. Let's suppose B was equal to A, boom, 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 all the way up through K. Okay. From here, we can see relatively quickly A is absolutely a subset of B because there's nothing in A that is not also contained in B. Great. Further, I would even go so far as to say that A is a proper subset because everything, because A is not equal to B. Now let's suppose that A actually went all the way up to K. Well, no, what we can do is let's make up a new set. Let's suppose C was A up through K. Well, then what we'd say is C is a subset of B. It gives me the possibility that they could be the same set. Okay? So just keep that in mind. It will be helpful later. All right, now, here's the notation we've got. We've got proper subset, subset equals, is an element of, is not an element of. Go ahead and take a second and fill out each of these statements and use the proper notation. I'll give you a second to do that. All right, so first, 3 is absolutely an element of the set 1, 2, 3. Okay, because that's the object contained in it. AB is a proper subset of ABCD. If you notice, I didn't use this notation because there's stuff in this guy, namely C and D, that's not in this guy. Okay? So make sure that you're using this notation properly. All right, now, for this one, the set containing 3, well, that's going to be a proper subset of 1, 2, 3. CAB is equal to ABC. You could say these sets are equal. Now, hey, if you really wanted to, another statement that's not false here, you could actually go ahead and say that CAB is a subset of ABC, and you are not wrong. Okay, so either or was totally acceptable there. For E, D is not contained in the set ABC. It's not an element of. Right? 1, 4, definitely not a subset because this guy has 4 in it and this one doesn't. Okay? Now, here's something interesting. The empty set. Is the empty set, what's going on with the empty set as it pertains to the set 1, 2, 3? Well, believe it or not, it's a proper subset. This set, whether you like to believe it or not, does have some nothing in it. And that's the nothing. Okay? If you've got something in you, that means you've got to have some nothing in you. That is a really weird thing to think about. Sets can get really mind-bending. Okay? So, we've got 3 pizza toppings. We've got sausage, we've got mushrooms, we've got peppers. I want you to notice that we don't have pineapple. That's because pineapple doesn't belong on pizza. Some of you may think it does, but that is ill-informed at best. What I want you to do is list all of the possible pizzas that you could order. Take a second and do that. Okay. For those of you who like pineapple pizza, you've likely gotten over the hurt of realizing that you've been mistaken. And the rest of us have listed all of our pizzas we could order here. So here's all of our possible pizzas. We have, I'm just going to go ahead and call sausage S, mushrooms M, peppers P. So the first option I have is a pizza with nothing on it, just cheese. This is one. Okay. Now let's do my one topping pizzas. This one could just have sausage on it. This one could just have mushrooms on it. This one could just have peppers on it. All right, now I'm up to 4. Now let's do my 2 topping pizzas. Sausage and mushroom. Sausage and peppers. And mushroom and peppers. All right. And now, since I can include the pizza with nothing on it, I also have to include the pizza with everything on it. So there are 8 pizzas here. Now, there are 2 key facts that we should be observing here. Number 1, the whole set is always a subset. If you think about this, what I've really done is I've asked you to construct all of the different subsets of S, M, and P. That's really what I've asked you to do. And what we notice is the set that's got everything on it, the universal set, all of my toppings in the universe with only sausage, mushroom, and peppers as pizza toppings, not so bad. I have to include the universal set. So the whole set is always going to be a set. Further, or the whole set was always going to be a subset. The empty set is always a subset. If I can include everything in the universe, I also have to include nothing in the universe because nothing is a part of everything. Okay? So let's suppose I only had sausage and peppers. Suppose I only had 2 pizzas. Go ahead and construct all of those for me. This shouldn't have taken you any time at all. We've got cheese pizza, nothing on it. Then we've got our 1 topping, which is our sausage and our peppers. And then I've got my pizza with everything on it. Okay. Again, I want to be clear that P does not stand for pineapple. Okay. Now, how many pizzas can be formed using 4 toppings? Take a second and do that one for me. So now we've got sausage, mushrooms, peppers, and tomatoes. I don't fully understand why one would put tomatoes on pizza. It's already in the sauce, but whatever. We start with the pizza with nothing in it. Well, nothing on it, rather. That's our cheese pizza. So that's 1. Then we'll do our 1 topping pizzas. So we've got our sausage, got our mushroom, got our pepperoni, and we've got our tomatoes. See, this 1 topping pizza, I feel like it demonstrates my point that tomato is kind of an absurd pizza topping, because if you just got a pizza with only tomato on it, then what you basically have is, I don't know, whatever. So now we'll do our 2 topping pizzas. There's not many things in this world I'm really passionate about, but I'm really passionate about pizza. So there's my sausage. Now we'll do our mushroom. And then we'll do our peppers and tomato. So then we've got 6, 7, 8, 10, 11. I'm missing something. So we've got sausage and mushroom, sausage, pepper, sausage, tomato, mushroom, pepper, mushroom, tomato, pepper, tomato. Yeah, okay, so then we're gonna do our 3 topping pizza, sausage, mushroom, pepper, sausage, mushroom, tomato, sausage, pepper, tomato, and then 13, 14, so that's when we drop out tomato, we drop out pepper, drop out mushroom, now we drop out sausage, mushroom, peppers, tomatoes. And now we include the set with everybody in it. Okay. Again, I cannot emphasize this enough. P does not stand for pineapple. Pineapple does not go on pizza. It's a silly thing that you would put on pizza. So we've got 16 pizzas here. I don't know about you, but I'm starting to notice a pattern. How many pizzas can be formed with n toppings? Well, we found if I had two pizzas, or two toppings, that gave me 4. With 3, I had 8 pizzas. 4, I had 16. N, it's almost like I'm taking each of these and multiplying by 2 as I add a new topping. So if I think about this, it's repeated multiplication, and I'm multiplying by 2 every time. This would be 2 to the n power. That's going to be an exponential function. Now, this isn't too crazy when we think about this, because really what's happening is, let's suppose we had, I don't know, 5 toppings, right? Suppose we had the number for 5 topping pizzas, and let's pretend we didn't know that it was going to be 2 to the 5th power. Let's suppose it was just some number x, right? Let's consider 6 topping pizzas. So what we've got is the 5 toppings plus or minus 1 ingredient. So the 5 topping we know is x plus 1 ingredient. Well, okay, so now we've got, just x, and then we say, okay, well, now we've added the 1 ingredient. Now let's take off that 1 ingredient. I get x. That's going to be 2 times x. So it's almost like if I know the number of, say, n minus 1 toppings, and I want to figure out how many pizzas there are with n toppings, I'm just going to take the number of pizzas from one less topping than it and double it, which is exactly what we're doing here. I understand that may have not sounded great, but that's pretty much what it is. All right, now, the way that I want you to take a look at the notes, we talk about the difference between sets and proper subsets, or how many subsets can be made from a set and how many proper subsets there are. Not terribly crazy. This is the number, this is an example of how many different subsets I can make with a number of sets containing n elements. And then for the number of proper subsets, you're just going to subtract 1 from it. Okay. So if I've got n of a has, we'll say, k elements in it, the number of subsets that I can make with elements of a is going to be 2 to the k power. Well, why does this make sense? Think of it like this. We're talking about there's k pizza toppings, right? So let's think of all of our pizza toppings here. We'll just number our toppings instead. We'll say 1, 2, blah, 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 all the way up to k. And what's going to happen is, if I'm going to make a pizza, well, so here's my pizza, and I've got cheese on it, and I've got sauce, I've got all the normal things on pizza. So let's consider topping 1. Do I want to put topping 1 on or not? Well, I have 2 choices here. I can either say yes or no. So I've got 2 choices for topping number 1. Let's suppose I say yes, okay? So I'll put 1s on my pizza. Now we get to topping 2, and we have a yes or no option. Let's suppose I say no. So I don't put 2s on there, but let's suppose for 3s, again, I have 2 options for 2. So for 3, I've got 2 options as well. Let's suppose for 3, I choose yes. So I've got some 3s on my pizza. So on and so forth. I want to know how many different pizzas can I make. That's what I'm really doing here. I'm going to find how many different subsets can I make. Well, what I'm basically doing now is I'm saying 2 times 2 times 2 times 2 times 2, blah, 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 a k number of times. Well, That's a 2 to the k number of pizzas that I can possibly make. Boom. So you can use that as an explanation there. Number of proper subsets. So remember, we said the number, what a proper subset is the original set without itself, or the number. So yeah, a proper subset is a subset which is not the original set. So this is the total number of subsets there are, and that includes the original set, which is only one set, so I'm just going to subtract 1 from it. Okay. All right, now, we're going to take sets and we're going to do stuff to it. Sorry about that. My cat was sitting outside the door and telling us her feelings. So, for operations on sets, for disjoint sets, we're going to start there. These are sets with nothing in common. Okay, that doesn't even look like a word. Let's get it together here. That's better. So, an example of 2 disjoint sets, boom and boom. If I had set A, set B, contained in my universe box. If they're not touching, they have nothing in common, these are disjointed. Now, let's suppose I had something like this, where it looked a little bit more like a Venn diagram. And I've got my universal set here. These are not disjointed. These have something in common. Now we're going to talk about those elements in common here in a sec, but for right now, we just look at A and B and we say, oh, they are not disjointed. Okay? Now, union. The symbol we use for that is U. Okay? You can think of this as the word or, and this is what we call an inclusive or. We'll talk more about inclusive and exclusive or when we get to logic. So we've got the set A union B. The way that we define this all elements, well, let's clean up our notation here. This is the set of all elements that are in A or B or both. Okay. So if I've got A, and let's suppose they aren't disjointed, just for fun. If I were going to do the union of these sets, what I'm going to do is color, well, if I wanted to show the set A union B, and I were going to color that in, it would look like this. Okay. It's everything that's in A, it's either in A, or it's in B, or it's in both. Okay. So here's an example. I've got the set A, B, and I want to union that with C, D, E. So let's start by listing everything that's in A. Boom, boom. A, B, and then we'll put it together with this set, C, D, E. Okay, cool. They didn't have anything in common. These sets are what are called disjointed, but it doesn't matter. We were unioning them together anyway. Basically, we're taking one box of things and another box of things and dumping them into the same box, and then we remove any doubles. Always make sure that you remove doubles. Now we've got M, N, and Q union with M, N, and P. So when I'm writing my union, I actually like to kind of take care of the things that are in common first. So I see that they both have an M, so I only need to write M once. I see they both have an N, so I only need to write N once. This one's got a Q, so I'm going to go ahead and write my Q. This one's got a P, I'm going to go ahead and write my P, and all is well. What you could do is just write a set and put MNQ, MNP in there, and then drop out the doubles. Sure, whatever works. Now I want to find A complement union B complement. U, my universal set, is 1, 2, 3, 4, 5. A is 1, 2, 3, so what's A complement going to be? Well, 4, 5. B is 3, 4, so what's B complement going to be? 1, 2, 5. So now, A complement union B complement, well, it's going to be 1, 2, 4, 5. 1, 2, 4, and then 5. 1, 2, 3, 4, 5. Union with the null set. What? So I take this set and I throw it together in the same box with nothing, and well, all right, I get that same thing. I don't even need to put nothing in there because it's assumed to already be in there. Okay. Now we're going to talk about intersection. The notation we use for this, bloop, it almost looks like a loopy A, which makes sense. We could think of it as and. So if you really wanted to, you could think of this as sort of like a loopy doopy A, but it's not. Okay. This means and. And the way that we could think of this is the set A intersect B, the set of all elements in both A and B. So if I had A, B here, their intersection, probably should have drawn them close together, be this little space here. Everything that A and B share, everything they have in common. Okay. Now, there's nothing to guarantee that every set has to have stuff in common, but we'll talk about that. So let's take a look at these two sets here. I want to know, what do these things have in common? Well, this one's got an A in it, but this set here, the BDF, does not have an A. So in its intersection, I'm not going to put A. But they both have a B. That's kind of cool. And now this one's got a C, but this one doesn't have a C. And these guys have D and F. These don't have D and F. There you go. That's the intersection. That's everything that they have in common. Now, same thing here. Construct my set. Well, this one's got an A. This one's got an A. All right, cool. So A goes in there. We've got B's in there. That's cool. And we've got C's in there. Okay. And that's it. Now AB intersects CD. Do the thing. There's nothing that these have in common. Nothing goes into this set. So you could quite literally just leave it as the empty set, or if you wanted to, with a little flourish, you could say, okay, well, the null set. The only thing they have in common is nothing. Same type of thing here. This thing here has 1, 2, 3, 4, 5 in it. This has nothing in it. Well, the only thing they both have in common is nothing. So there you go. Now, for part C, this is a perfect example of disjoint sets. They're disjointed, that they don't share anything. Same thing as D, okay? That is everything that we need to know for set basics.